Hello, welcome to Certificates 101. I'm Michael C. Bazarewski, an engineer in the Microsoft ISV and Digital Native Center of Excellence, and the owner of the eCertificates lesson in the IoT Production Training Pack, available at https://aka.ms IoT Training Pack. There's a selection of modules available to help you get your solution from a basic proof of concept to a full production deployment. This video is the companion to the Certificates module. The purpose of this module is to supply a basic understanding of how digital certificates work, the concepts that drive their use. This will not just be focused on Azure Internet of Things use cases, but will also be more general and broad. Other modules address IoT edge use cases and other use cases. I'll start with a certificate example that everyone encounters daily without necessarily thinking about it. Nowadays, many websites, and certainly all offering purchases, offer HTTPS capabilities, which are web connections over a TLS, Transport Layer Security connection. But what is actually going on to make this happen? The underlying technology here is something known as asymmetric or public key cryptography. What public key cryptography solves is the problem of how to exchange a key safely for encryption and decryption. It does this through the use of clever mathematics involving large prime numbers, where a pair of keys, known as the public key and the private key, are used for encryption and decryption. As an example, let's look at Alice and Bob. Those names are commonly used in examples around cryptography. Bob wishes to send Alice a confidential message, in this case the word hello. Because Alice has made her public key available, Bob is able to use it to take his message and encrypt it. He then transmits that encrypted message to Alice. This can be done in an open way because the message is no longer plain text. Alice then decrypts the message with her private key. Because of the way the encryption algorithm works, only the private key can decrypt what was encrypted with the public key. This is actually the basis of TLS as well, where the client generates a bulk symmetric key and transfers that to the server through asymmetric encryption. As long as the shared key is large enough and rotated frequently, this is a safe system. Asymmetric cryptography also works to support digital signatures, where a document can be hashed and then the hash is encrypted with a document owner's private key. Anyone can validate the signature by decrypting the signature with the public key and comparing the document's hash to a computed hash. This table summarizes public and private keys. It's present in the online documentation that goes with this video for your future reference. Clearly, part of this system is the distribution of public keys to clients. This is where we actually get to certificates. Certificates are a representation of key information and related information, such as the subject, which is the identity the key is assigned to. In the case of TLS, this is generally used to match the name to access the website, such as www.microsoft.com, and match it with the subject name in the certificate. If you think about it, the certificate by itself would not actually be enough to guarantee safety. This is because there would be no way to know if the certificate was believable or trusted. In other words, what's to stop a malicious actor from generating their own certificate for, say, www.microsoft.com and pretending to be the real Microsoft website? The answer lies in a concept known as the chain of trust. To be trusted, a certificate must be signed using the digital certificate concept mentioned earlier. That signature has to come from a certificate authority, or CA for short. The certificate authority can be trusted directly by a device, but it's more common for an intermediate CA to be trusted and to sign that certificate, where that intermediate CA has had its certificate signed by a parent certificate. In this way, you walk a chain of trust. Eventually, you reach a top-level certificate known as the root CA. The root CA has a self-signed certificate, which means that it states it trusts itself. Self-signing, though, means there's a problem, because how can a device trust a self-signed certificate, where the certificate essentially just asserts it can be trusted? This is up to the device administrator and/or software manufacturer to solve. Any device that will trust the root or any of its children must have the collection of issuing CA certificates in what is referred to as the trusted root store. The root store in any device or runtime that supports TLS will include a collection of roots that have been deemed as safe and well known by the software or device maintainer. For example, Microsoft ships a collection of trusted roots in Windows, and Mozilla ships a collection of trusted roots in Firefox. The industry works in a cooperative fashion to manage the trusted roots trusted by different devices and software runtimes. Besides these trusted roots, it's possible for a device or software administrator to manage the trust list by adding, or much less commonly removing, entries from the list. The most common use case for this is private enterprise CAs, where someone, such as a device manufacturer, runs their own CA for internal or device purposes. In all cases, the certificate chain must be trusted by the device for the device to trust the service's certificate. Similarly, if the device is using a certificate issued by a private CA for device identification, such as to authenticate to Azure services, the service must trust the device certificate. In other words, in the case of any transaction where certificates are involved, both sides should trust the certificate chains for the certificates used on both sides of that transaction. So that explains what the chain of trust is doing here. But that's just part of what we refer to as the certificate lifecycle. So I'm going to spend a few minutes now reviewing that idea because a big part of maintaining an IoT device is maintaining its associated certificates. There's 4 primary stages in the certificate lifecycle. They are certificate enrollment, certificate validation, certificate renewal, and certificate revocation. The first stage is certificate enrollment. The process of certificate enrollment is the generation of a certificate signed by a certificate authority. It's how a certificate for a service or device becomes real. The process is as follows. First, an administrator, which could be a person or it could be an automated process on a device, requests the device create a public-private key pair. Second, the administrator requests the device generate a certificate signing request, or CSR, tied to the public key of the key pair. Notice that the private key remains exclusively with the device and is never sent to the CA or to another party. Third, the administrator sends the CSR to a certificate authority, CA. Fourth, the CA validates the entity using whatever processes are used by that CA. Depending on the certificate type and the issuer, this could be something simple like looking up an entry in DNS, or it could be something as complicated as looking up a business license and validating that business license. Fifth, the CA creates a signed X509 certificate, as described earlier. Sixth, optionally, the CA notifies the administrator of the issuance out of band. This is typically for human processes versus automated processes. Seventh, the administrator retrieves the certificate from the CA and then last installs that certificate on the device. This leads to a natural question. How do administrators and developers store and transfer certificates? Often, this is through the use of certificate files. Note this is not always true. Sometimes a service, such as Azure Key Vault, stores a certificate. But it's more common, especially during development, to deal with files. There are many ways to store certificate files, but there are 3 that are most likely to be seen by developers. The first is a PFX file. A PFX, or PKCS number 12, the formal name for the format, is a binary format that supports holding both a private and a public key, with an optional password protecting the private key. It also supports holding an entire certificate chain, up to and including a root CA public key, which means a server using or importing a PFX file can present the entire chain for validation by a client. As described in the X509 content earlier, a full chain to a trusted root is required to perform proper validation. As an aside, technically PFS is not exactly the same as PKCS number 12, but in common practice, it's not unusual to see the terms used interchangeably, although PFX is much more commonly used as the format name. This file format is the typical file format seen in Microsoft Windows and in Microsoft Azure. Next is a PEM file. A PEM file is a base64 encoded file that acts as a container for one or more base64 encoded certificates and keys. This format is very common. For example, it's used by Nginx. Because the format is essentially just a text file format that stores one or more base64 encoded objects, it's very flexible. It can store a public leaf key or a certificate chain or just a private key or some combination. These are sometimes seen with the CRT extension. For example, OpenSSL commonly uses that extension, or the CER extension. For example, on Windows, if this format's being used, it's commonly seen with the CER file extension. Other common use cases for PEM files include SSH, where SSH tools, such as OpenSSH, generally store their public and private keys in separate PEM files. For example, the SSH ID RSA file is a PEM file that represents an SSH private key, while the ID RSA pub file represents an SSH public key. The third file format is P7B. P7B files, or PKCS number 7 files, are base64 encoded files that store only public keychains without private keys. They are seen in both Microsoft Windows and Java environments. But now back to the lifecycle. The next stage of the lifecycle, the one that is most commonly seen as part of the lifecycle, is certificate validation. When a certificate is presented by an entity to a client, the certificate status is validated to verify that it's issued by a trusted CA, a CA that is in the trusted root store or is issued a certificate from a trusted root or trusted intermediate. Its listed identity, such as the certificate's subject, matches the entity's presented identity. The certificate isn't expired, which I will discuss more later. It isn't revoked, I'll discuss this more later. And its issuance has been logged properly if applicable, and again I will discuss this more later. Certificate validation is a complex process, and applications typically use APIs or libraries such as OpenSSL, the Windows Crypto API, or the Java JCE to perform the validation. Here's a high-level overview. First, the CA chain is constructed from the presented information. Constructing the complete certificate path requires that the validator is in possession of all certificates in that path. This requires the validator keep a database of intermediate certificates or that the protocol using the certificate supplies the necessary intermediates. In the case of TLS certificates, a server will typically present a complete chain, including the server certificate, the intermediate CA certificates, and the root CA certificate as part of the TLS negotiations. Second, validate the root certificate is trusted by comparing it to the list of certificates in the root certificate store, the trusted root store, to ensure the entire chain is trusted. Third, check the validity dates and constraints on the certificate. This means checking to make sure that it's in its valid date range. Certificates have a not before and not after date, indicating when it's valid to be used, and any constraints such as the certificate may be used for code signing, or the certificate may be used for server identification, or the certificate may be used for device identification, and validating that the constraints are all valid. Fourth, check to see if the certificate is revoked. Certificates may contain extensions or extra pieces of information to indicate a certificate revocation list, storage location, or a service such as an online certificate status protocol responder or OCSP responder. These methods allow the verifier to check that a CA has not explicitly revoked the certificate in question. I'll talk more about that in a little bit. And finally, if it's available, check the certificate authority's issuance log. Modern certificate authorities are expected to host a certificate transparency or CT log that clients can check on a regular basis. Note that I'm deliberately oversimplifying this whole process for the purpose of this video, but there's more references in the written documentation that accompanies this video, and as I mentioned, a library will often handle this for you. There's other topics in the documentation around certificate validation as well, such as the concept of certificate pinning. For the sake of simplicity and time, this video does not discuss certificate pinning, but it's discussed in detail in the documentation, including the pros and cons of certificate pinning and concerns to be aware with respect to it. The third certificate lifecycle stage is certificate renewal. As mentioned earlier, certificates have expiration times that are associated with them as part of the maintenance of the certificate. It's a way for the CA to continue to validate the identity of the holder of their certificate, as well as to allow updating the certificate with new cryptography algorithms and the like as time goes on. For example, replacing SHA-1 certificates with SHA-256 certificates. Any device or service working with certificates needs to have a way to have new updated certificates installed or rotated in, including potentially a way to request the replacement certificate in the first place. Certificate rotation, while not something that occurs frequently, is critical to the health of a service or device. This is often done through either device software updates or through scheduled update processes on the device or service itself. It's critical that a device creator understands how to handle this, including how to do quote-unquote emergency renewals, such as in the case of certificate revocation. Certificate revocation is that final stage of the four. This does not come up very often, but it does come up as mentioned earlier when I talked about validation. There are times when a certificate must be labeled invalid. This could be because a device or service has been compromised, causing a private key to leak, or because the certificate authority itself has been compromised, causing a certificate to be issued that should not have been issued. There are other cases as well, but again, it's not that common. The important thing is that this goes back to the validation steps, where proper validation checks to see if the certificate is revoked or not. Certificate authority administrators need to manage this as part of their tasks. With that, I've finished a non-IoT specific view of certificates. But what about the IoT specific use cases? If I go back to the IoT architecture picture again, there's multiple areas where certificates are involved. Let's start with the IoT service side. The Azure IoT Hub and Device Provisioning Service, DPS, support and indeed require connections using TLS for both the control plane and data plane. This is true for all three data plane protocols, AMQP, MQTT, and HTTP. This means that all devices connecting to the services need to support TLS, including having an appropriate trusted root store configured on the device. The product documentation has more details on what appropriate entries look like for the Azure use case. But what about the client side? The client side may or may not have a certificate depending on the way the client authenticates to Azure IoT services. For DPS, there are three ways for a device to authenticate: a shared access signature token built on a shared password or symmetric key associated with the device or the enrollment group, a trusted platform module nudge challenge, and X509 certificates. Because SaaS tokens are built on top of shared secrets, they do not apply to this discussion. If you're familiar with TPMs, you may think that the TPM nudge challenge is going to come up for the certificate conversation. For the TPM nudge challenge, however, certificates are not involved. Instead, a transaction tied to the unique hardware identifier burned into the TPM is used for authentication, not a certificate. This leaves us with the use of X509 certificates, as I've talked about so far. In this scenario, the device has its identity tied to a certificate on the device, which can be registered through an individual enrollment, where the public key is distinctly listed, or an enrollment group, where the issuing CA is indicated. In either case, it's important that the device keep the private key for the device protected, which ideally would be in a hardware security module, or HSM for short. Physically, the HSM may be part of a TPM. There are definitions that state a TPM is an HSM, but the industry is not consistent on this point. It may be tied to the processor, or it may be a standalone HSM. Although there are less secure methods of storing a certificate on a device, Microsoft discourages insecure certificate storage. That said, where does the certificate of the device come from? There's different patterns that apply. One example is for a device manufacturer to install a certificate at assembly time, where as part of the factory line, the certificate is installed from a CA accessible from the line, or from a collection of certificates pre-generated and installed on the line. The pre-generated use case is very common because it avoids the CA being a fundamental point of failure for the factory line. Another example is for the device to boot without a certificate, and as part of initial provisioning, have the device request a certificate from a device-specific service. This could authenticate using a unique one-time password, a shared password, or even something like the MAC address of the device or serial number of the device. The service then generates a certificate for the device and sends it to the device as a response to the service call. The device then uses that certificate for all Azure IoT service calls. As of this video's production in July 2023, there's not a public DPS-based service that offers this capability, but some customers have created their own custom services for this purpose. Moving on to IoT Hub now, there are two authentication mechanisms supported. The options are SAS tokens, which are generated based on a symmetric key, a per-device password, and an access policy that's defined on the hub. A SAS token is only valid for a limited time, or an X509 certificate that is set per device. The SAS token is not certificate related and thus does not apply to this video. If using DPS, the registration process against IoT Hub automatically provisions the certificate reference in IoT Hub against the certificate that was used in DPS. If not using DPS, it's up to the device software administrator to manage the appropriate IoT Hub registrations with the appropriate certificate references. There's a lot of concepts that overlap with the already discussed certificate concepts and DPS concepts, and there's no need to repeat those here. The discussion of IoT Hub completes this journey through the introduction to certificates and how they interact with the basics of the Azure IoT solution. Please refer to https aka.ms IoT Training Pack to access the full training pack, including the written documentation that accompanies this video with more details on the processes covered here. Thank you for watching, and I hope you found this video useful.